Hi, and welcome to the Signal Path. In one of the previous episodes, I did a repair of a Keysight MXA. That was model N9020A. It was a 26.5 gigahertz instrument, and that was generously loaned to me by Alltest. Alltest has a huge inventory of test and measurement equipment. They do their own repairs, calibration, and various services. You should definitely check them out. They've been very nice, allowing me to work on this equipment. And then they asked me, well, what do you want to work on next? And I said, well, do you have any millimeter wave high-end synthesizers that don't work? I'd like to take a look at one of those. And they said, well, how about an Agilent E8257D? This is a PSG analog signal generator. These are very high-end units. They can go all the way up to 67 gigahertz and cost over $100,000. And of course, this one doesn't work, unfortunately. And the reason it's called an analog signal generator is because it doesn't have vector modulation built into it. Vector modulation adds a huge additional cost to these, and of course, will give you complex modulation capabilities on the RF output. Makes it much more useful for a really wide range of application, wireless included, of course. So the unit here is fully booted, and it doesn't really show anything wrong. Everything seems to be working. The oven error that shows up because the crystal oscillator is warming up is not there. And they're saying that there may be a problem with the 10 megahertz output, but obviously that doesn't affect the internal PLLs because we don't get any unlock errors or anything like that. We can go ahead and set this to, this is the highest frequency this goes is 31.8 gigahertz. So we can go ahead and have it at 31.8 gigahertz, and I can change the amplitude to 0 dBm here. I'm going to enable it, and let's see what happens. So here's the output. There you go, RF on. We don't get an unlevel error here. So that seems okay. So what's wrong with it? Well, there used to be a sticker on top of this, and I took it off, and the sticker said, do not connect to any other instrument. Be very careful because there's something wrong with the output. So that's interesting. So they don't want this to be connected to any other instrument, obviously, because they don't want to damage something else. So we have to be very careful and do some investigation on that. But really, the GUI doesn't tell us anything. It seems to work just fine. We have to do some further testing. So let me reposition this and connect it to some spectrum analyzer. So here's our test setup. In order to protect the instrument, particularly the spectrum analyzer that the synthesizer is connected to, I have a bias T here. This is a 50 gigahertz bias T, and the output of the bias T is connected directly to this multimeter. So we can measure any voltage that may appear at the output of the port of this unit. And then after that, we're of course AC coupled, and that goes onto my Keysight MXA up there. And the Keysight MXA is set to a 30 dB into input attenuation just to make sure that it is protected. You really have to respect the DC isolation between these high-end instruments. And if you look closely underneath any of the connectors, for example, this connector over here, it specifically says 0 volt DC. And there's a reason for that, because if you put DC into it, you will destroy the instrument. And the same with synthesizers, same with high-end spectrum analyzers. When you AC couple the input of a spectrum analyzer, you're actually making things considerably easier in terms of the design, in terms of protecting the unit. That's why sometimes you see 30, 40 volts is allowed. But of course, your low cutoff frequency is affected. The MXA up here has an input low frequency cutoff of 10 hertz, and that's often not done with the capacitor. And some of the really high-end instruments go down to 2 hertz and definitely have to be DC coupled. Okay, so enough of that. Let's go ahead and turn the instrument on. So it's right now turned off. And by the way, I took the cover off. This thing was full of dust. I had to take it to the garage and do air blast all the dust out of it, but now it's good. Let's go and turn it on. And, oh, look at that. That is not good. So we are seeing a 0.8 volt DC appear at the output of the instrument. That is not what we should be seeing. You should see always 0 volts. And right now on the spectrum analyzer, there's of course nothing because there's no RF signal. So before we even configure the instrument, before it's even boot fully, we already see this voltage. So this is coming from some static bias somewhere that shouldn't be there. That's going to be an interesting thing to find out. Oh, it just went to 0. That's interesting. I heard a relay click. So perhaps the output is disconnected. So let's wait a little bit for it to fully boot and then try some RF signals. So let's investigate this a little bit more. So the instrument is right now set to 31.8 gigahertz. I'm going to preset this. I'm going to set the frequency to 1 gigahertz. There you go. You can see we see no difference. So of course the attenuation being set to 135 gigahertz with a mechanical attenuator would kill any DC offset anyway, because it's DC coupled and it would load the output and it would attenuate everything from DC, and 135 dB is an enormous amount of attenuation. So let's go ahead and change the attenuation. I'm going to set the amplitude to 0 dBm. There you go. And check it out. We're back to minus 0.8 volts. Actually, it used to be plus. Interesting. I think that was because it was higher than 1 gigahertz. So we have to really do this systematically. Let's do one at a time. So the output right now is not even enabled. If I enable the output, we see absolutely no difference. But the fascinating thing is that on the spectrum analyzer, I actually see the output. I'll show you it in just a second. This is really strange. So I'm going to disable the output. This doesn't seem to be making any difference on the output anyway. And I'm going to go ahead and increase the amplitude. Remember, the output is not enabled. This is just so that the attenuator will be disabled. Let's go up. There you go. And oh my goodness, minus 13 volts. Wow. So that tells me a lot. So when I go above 6 dBm on this instrument, the input attenuator, which is a mechanical attenuator here, is basically completely disabled. It's in a through mode, so 0 dB. That means that any voltage that appears at its input will appear at its output. As soon as the attenuation kicks in, you're going to get some voltage division, and that's going to show up here as well. And also it will begin to load the input. Right now at DC, the output of this instrument is not loaded. It's only loaded into 10 mega ohms, which is for the multimeter. So at the unloaded DC offset of this instrument with no attenuation is minus 13 volts, which is enormous. If I go and bring the attenuation down, as soon as the attenuator kicks in, we're back to this. And if I keep going, you can see that it will constantly go down as different attenuation settings kick in. So let's go back to 10 dBm here. So we see the attenuation open, and I'm going to change the frequency instead. So let's go over here. Wow, this button is really stiff. So 1 gigahertz, 2 gigahertz, 3 gigahertz, no difference. 4 gigahertz, there you go, that's what we were seeing, 0.8 volts. So as soon as we went above 3 gigahertz or so, we started seeing this, and I can find out exactly what that frequency is. That's no problem. I can continue going up, and yep, doesn't seem to make any other difference. Nope, all the way up to 13.8, 31.8, go back down. There you go, 800 megahertz, we're back to minus 13 volts. Okay, so we have a few interesting symptoms. With the attenuator open, below about 3 gigahertz or so, we get minus 13 volts, and above we get plus 0.8 volts. Very unusual. So now let's go and take a look at the spectrum analyzer and see what kind of signal comes out of this from an RF point of view. So I just realized that this other error showed up here, which is the Yig oscillator loop unlock, and that's bad. That's yet a totally unrelated problem. At least I think it's unrelated. So now we have this Yig problem, which is unfortunate. So let me go ahead and see if I can clear the errors. Let's see, what do we have? Reference unlock. Yep, that may explain the part of the 10 megahertz problem that I also was told it has. So yep, it has more than one problem, and that was a multimeter turning off. Yep, so now you can see this unlock over here. That's really annoying. So we actually have two totally different problems to debug here. So anyway, I think the output voltage part is first. We have to adjust that, because even with the output not enabled, you have that issue, and that has nothing to do with the synthesizer portion anyway. That's the output driver portion, so we have to take a look at that separately. Okay, so the output is set to 10 dBm, and it is set to a frequency of 1 gigahertz. There we go. So I'm going to enable the output. Let me see, here's a 10 dBm, make sure it's all correct, and there you go. Look at that, it's there. And the frequency may not be exactly correct anyway. The instrument says it's unlocked, but it's very close to 1 gigahertz, and the amplitude is correct. So that's really strange. We're getting a DC voltage at the output, an offset DC voltage of almost 10 volts and minus 13 volts, and we're still getting a perfect RF output. It's just strange. So let's go to higher frequencies. Now this cable I'm using is certainly not rated for these frequencies to go above a couple of gigahertz, but here's 3 gigahertz, and then to 4 gigahertz when the output changes to 0.8 volt offset, and you can see it's still correct. And I can keep going, and the amplitude is going to drop, and again that's because of the cable, but there you go. Here's 25 gigahertz all the way at the end. It's supposed to be 10 dBm. Of course it's not. This cable is terrible. It's definitely not rated for this, but yeah, you can see that the output is working. How strange. I think we should really take a look at the block diagram and see if we can decipher what could be wrong before we take the instrument apart. And here is our block diagram for this instrument, and it is beautiful. I don't think there is any other test and measurement vendor in the world that provides as much detail and sophisticated service manuals like Keysight does, and I really appreciate that. This shows a great deal of respect and connection with their customers, and I hope that other vendors would follow suit. So if you look at this here, we can see that this has everything in it. That includes the fractional ends, the outputs, the LC section, pulse and analog modulation, the Yig driver portion, and various doublers and modulation components. So these are all different microwave blocks, of course, so we have to focus on the ones we think are problematic. And then if we get other units, we can look at other sections. So we know that the 10 megahertz doesn't work, so we're going to leave that to the end, because the output voltage problem is now the most important, which means we have to focus on the output portion. So let's go over here. I'm going to zoom in to some reasonable amount. I think this is good. And then we're going to find the output connector. And I see it right here. Here you go. Here's our output connector. So this is where we have connected our bias D, and that's where we see the voltage. And the very first thing it sees, this is optional attenuator. This is an electromechanical attenuator, and our instrument does have this option enabled. And I believe that that's because we can go all the way to minus 135 dBm. So this normally wouldn't be able to do that otherwise. I think you can only go down to minus 20 without it. So that's very unlikely to be the source of the problem. These are electromechanical, these are not solid state. For voltage to leak from this to the output, something drastic would have to go wrong inside for the basically cold driver voltages to leak in. So this, I would say, very unlikely. The next block is this coupler. This coupler is a directional coupler along with the detector used to feed the ALC, which is right underneath here, to level the output to a desired value. This, I also say, is most likely not the problem, and the reason is because this is again a directional coupler, and it's not really DC coupled anyway, and the chances of this leaking voltage is very, very low. And the next thing we hit in the chain is the first part that has potential of causing problem, and that's because this is our first solid state component that does some frequency translation, and it has solid state components in it. We're talking about the E8257D GHz doubler. So this block diagram is for the instrument that goes all the way up to 40 GHz. Above 40 GHz up to 67, things change drastically and the output portion is quite different. So this thing has three connections. It's J1 here, J3 here, and J2 here. And the J2 is of course the output, so that's the part we're going to focus on. And then we have to see what J1 and J3 are. So this is a doubler, and as the name suggests, it will double any frequency coming into it. This is normal. A lot of these synthesizers generate frequencies, lower frequencies, and then they double them or quadruple them and then filter them in order to give you a pure tone. So here our 40 GHz doubler has two inputs. The input between 10 to 20 GHz goes through the doubler, and it can become anywhere between 20 to 40. Now this instrument only goes up to 31.8 GHz, which means this 32 to 40 GHz portion is not enabled. And I think this is just a software thing actually. And you can see there's a tunable bandpass filter here built into it, it looks like. And that is to basically when you are using the 32 to 40 GHz in order to filter this. So I don't think this is even really engaged in any meaningful way. Oh no, maybe it's always on actually, I take that back. This is always on to filter the higher harmonics. So you can see that we have a switch here. And that switch is controlled by this signal over here, and that switch can always either select this, which means signals between 20 to 40 GHz have this signal flow, and the signals below that come from here. So now we can see that there is another input, and that input goes between 250 kHz and 20 GHz. So signals all the way to 20 GHz are all using this path, and as soon as you go above that, then it switches to this path. So we know that the problem exists in all these frequencies anyway, but it gets worse around 3.2 GHz. And let's see if that would make sense from the block diagram. So the previous stage to this is the modulator filter section. And in that, you can see that indeed we have a path going in here that is limited to 3.2 GHz. So this solid state switch here can choose 3.2 GHz, 3 to 5, 8 to 13, 13 to 20, and 5 to 8. And it can switch between all of these. So something is going on. Now, looking at this, I'm beginning to suspect that the problem might be either here or here. And the reason I say this is because we see a voltage across all frequencies. So all the bands show it is much more at low frequencies below 3.2 GHz. And that's the low frequency path is this one. So what we should do as a starting point is to identify where this is, disconnect everything after it because we don't care, and measure the voltage here. Do we see the same problem? If we do see the same problem, then we will move a step back. We will take this cable, measure it, we will take this cable and measure it, and see if these guys have any DC offset. If they don't have any DC offset, then the problem is just within this doubler section, and then we can take a close look at it. So this is now becoming fairly clear of where we should attack. Now if I go further out, you can see all the way over here, we have the entire YIG driver section. So the YIG unlock problem would come from here. You can see a 10 MHz reference enters the instrument here. And if this 10 MHz reference is not working correctly, we're going to have a whole bunch of problems. So I'm not going to analyze this yet. I would like to see if I can fix this problem, or at least identify what the problem is, and move from there. Okay, let's go ahead and take this top off here. There we go. You can see different boards are all mentioned over here at the top as well. And here you go. Yeah, very nice. Very Keysight classic design here. So we have our power supply here. Here's the oven controlled crystal oscillator. Unfortunately, the screws are missing. You can see right over here, this is on some rubber grommet for absorbing vibration. That means someone has worked on this, and unfortunately they hasn't put the screws back, so that might be a problem. There's some issue here. Anyway, we have to come back to it. All the different boards here, we don't need to look at them, but here's the front end section, and I think it's worthwhile zooming into that area a little bit, because that's the first section we're going to pay close attention to. And I already recognize all the major blocks we need to pay attention to here. Here it is. Here's our main attenuator. So the bottom of this attenuator is the output, which then goes directly to the front end connector. The front end connector is right underneath this. Here's the front of the instrument. This I'm not sure what component that is right now, but here's the directional coupler. You can see the directional coupler's output goes directly to the attenuator. Here's a detector here connected with this cable going into one of these boards, and one of these boards is must be the ALC board. So this directional coupler, again, is most likely not the problem. The input of the directional coupler comes from this block, and I can see from the connections here that this is most certainly the doubler. So that's the first block we're going to pay attention to by disconnecting it directly from here. And these are the two other inputs. One of them is the 3.2 gigahertz one, the other one is the 10 gigahertz input or so. So disconnect this, take a look at see if the voltage is still present here. Okay, so I set it up, I disconnected the cable, and a couple of points for you to be careful. So again, this is a V cable. This is not just a regular cable. You cannot bend this out of shape. This is designed and only designed to be used for this. So you have to be very careful removing this, and of course I have replaced it with a V cable going into another V type 50 gigahertz bias T, and the output of the bias T is connected to the multimeter. So everything is turned off now. So I'm going to turn it back on, and let's see, there you go. We see exactly the same 0.8 volt. So that verifies that the entire front end, coupler, ALC, all that has nothing to do with the offset, and that's exactly what we were expecting. That verifies. I'm going to turn this off because the ALC is not connected anyway. So the next step is to figure out how to deal with this doubler component right here. And there's a few things we can do. We can try removing it and then see if there's a long enough cable to operate it remotely, because I certainly cannot poke around with it while it's connected. I also have to trace these two cables from the back of the instrument, and we can access them and separate them and measure them independently, and that would also be very helpful. So here we have the back of the instrument, and the back of the instrument has a few other connections to the front as well as the back of the motherboard you can see here. So the two connectors that go to the front end doubler are here, and you can see this is the other side of the attenuator. This is the attenuator plug that powers it and so on, and we can see the output of the attenuator that goes to the front of the instrument. So we're basically looking at the bottom of that. So I'm going to disconnect this, and that's going to give me the two connections to measure, as we said, based on a block diagram, and we can see if these produce the correct signal and if they have the correct DC, although they should really not have any DC because the output of these both go through quite a few other circuitry anyway. I just want to make sure that these are working. Okay, so here I have connected the instrument to the output of this unit here, which goes from 250 kilohertz to 20 gigahertz. So this is the path that doesn't need a doubler. It still goes through the doubler block, of course. And the other output that goes from 10 to 20, which then gets doubled to go to 20 to 40, is right now connected to nothing. So right now we're having this connected to the bias T, and then we're connecting it to the Regal spectrum analyzer there. This only goes to 7.5 gigahertz, but that's okay. We just want to see a tone there. I thought it's a little bit easier to see everything in one frame. So I'm going to go and turn this on, and we should expect good operation from this, no voltage and so on. Let's see. Wow, look at that. That is surprising. The fact that I see the same DC voltage at the output of this block before the doubler really is surprising, because it means that this is forwarded through the doubler block. So let's wait for this thing to boot, and then I can go through the frequencies and see if I can reproduce the 13 volt offset here, because then that would verify that it's coming from here, which again I'm really surprised to see. So we'll have to take a closer look at the operation of this unit right here, but let's wait to see if I can get 13 volts. And check it out. Indeed, I can produce the same offset here. So yep, there's something going on with this block right here that's producing such a large output DC voltage. And if I change the frequency, you can see that frequency is actually present, which again is consistent because we were seeing the right output before. So the frequency works, but the DC offset is there for frequencies below 3.2 gigahertz, and then it switches to 0.8 for frequencies above that. So given our surprising result, we're going to have to move further back in the block diagram. So we can, for now, eliminate this as a problem, because we saw the DC offset even without it. And this is the point I just measured, by the way. So we saw that that problem exists, which means that whatever's in here is actually forwarding DC as well as RF. And that makes sense because that's consistent with the measurement. So now we have to look at the modulator filter. Again, we have to do the same line of reasoning. The problem could be from inside of this, or the problem could be coming from somewhere else. So that means that this path is now a suspect path. So we have to follow this and see if this path exhibits a similar problem. I don't know if this option is in there or not, but the 3.2 gigahertz. So the J3 input of the A30 modulator should only have signals which are between 0 to 3.2 gigahertz. We know that that's from this portion AA output. So let's go and isolate that and measure this, do exactly the same thing and see if this has a problem. If it does, then we have to move into this block, and if it doesn't, then the modulator problem is the point we have to take a look at. And here is our sub 3.2 gigahertz path. I've tapped that cable out over here and I've connected it the same thing. You can see we have our signal and there is no DC offset. So the sub 3.2 gigahertz input is not causing a problem. I'm going to do one other test. I'm going to check the other input as well to make sure that doesn't have a DC offset. And if that one's also okay, then the problem is being generated directly in here. And this is the output I measured. And you can see if I switch them, if I go ahead and remove this connector from here and connect the output once again, even with nothing connected to the 3.2 gigahertz port, you can see that we will indeed have the same problem. So the DC offset is present even when the sub 3.2 gigahertz cable is not even connected. So I'm just going to do one other test here to make sure that's not an issue neither, and then we can turn our attention to this block and find out why it's doing that. And here's our last test measurement here. You can see I'm taking the output from a different block now, which was going into this. This is the over 3.2 gigahertz, and you can see we're having a signal in the 4 or 5 gigahertz range right now. The signal is present, no DC offset. So that pretty much really narrows everything down. So we're really dealing with a problem most likely in this module, the modulator filter portion. So I'm going to take this out so we can take a look at it a little bit closer and making sure that, of course, we understand its inputs and outputs. Okay, so here's the module, and you can see various different ports in and outs that we were measuring. I believe this was the output, if I'm not mistaken. Yeah, it says RF out right next to it, so that's where the problem is. Now this has a very typical construction, the construction of an RF module in the back, like so, that goes through pins and attaches into this board. So all the control and analog biasing is done on this, and this just houses a lot of RF components. And this is really weighs quite a bit actually. So I think the next step is to obviously open it further so we can take a close look, especially take a close look inside underneath this module and see what's going on in it. You can buy one of these modules as a replacement for a few $1,000s. It's still fairly expensive. Of course, the unit is worth much more than this. But nonetheless, I want to take a look and see if there's anything obvious that we can tackle, although I'm a little bit skeptical, but nonetheless, finding the problem in this is already quite valuable. So let's see what we have here. I've removed all the screws and gotta be careful. There we go. Oh, look at that. That is beautiful. Let me take the gasket off. This is for hermetically sealing. Gotta be very careful. Yep, as I suspected, a whole lot of chip on board. Everything is wire bonded. We're gonna have to look at this a little bit under the microscope. So it looks to me like here's the output portion. These are all the different filter sections that you can see then combine into this. So this little mimic module, well, this little module with mimics on them, it combines the different bands, and a final switch is on this. So the flow must be somewhere out here, I believe. I mean, unless something else in here is broken, which I doubt it because it only shows up at some frequencies. So let's go and take a look at this maybe a little bit more under the microscope. You can see the different bands coming in, the low frequency, high frequency getting combined, switches, all the different bands. It's very beautiful. So let's look at this module under the microscope and do some reverse engineering and see if we can figure out how it works. We're looking at the very output of the module, where all the signals combine and go to the final destination, which is a single SMA output. So this is the output right over here. You can see all the different paths that come over here and combine. These are all appear to be pin diode switches. So this is the output. You can see some filters in the way. We're looking at the sub 3.2 gigahertz path and all the other paths that go through bandpass filters. So that appears to be this section. So right over here is basically this portion right here. You can see we have our switch that selects between the different bands. All the different bandpass filters. We have the sub 3.2 gigahertz signal coming over here. So they all reach the same point. And that's exactly what this section over here is. So we can follow the sub 3.2 gigahertz signal and see where it goes. Now it comes from the top over here. We can follow it. You can see a straight piece here over ceramic. Here's some filter. This is most likely a low pass. Here's some more. LC with bow tie on ceramic. We continue down, and here's the input. So it looks like the 3.2 gigahertz path is a direct connection And I measured that already when it was in the instrument. So this point did not have the voltage, which means whatever is feeding this is fine. Whatever is happening in this module, therefore. So the problem is almost certainly in this component here. But we can also follow all the other paths, all the different bandpass filters. We can take the ones down here. Follow, you can see one over there. We follow here, there's another one. This is the lowest frequency one, I think. You can see some big bow tie stubs there. Come back all the way, it comes back over here, and then here's the splitter. Here's where the signals split. So the input comes in, we got one bandpass, another one, another one, another one, and this one directly goes to the output. This is a 10 to 20 gigahertz output, which goes into the doubler, which then ultimately goes to 40 gigahertz. This doesn't go through any filter, and this path is working, so we have no issues here. So we go back, we can see here some broadband Wilkinson power combiner, 2 distributed PAs, broadband Wilkinson splitter. So this is a power combining PA, identical input and output, or I should say very similar input and output. All the biasing of the different distributed amplifiers are all here. Another pre-driver here. Again, you need to boost this signal because you need to produce a lot of power, of course. Once you output this, you don't have any more chance to do it. So you have to have quite a lot of power. Here goes some more filtering over here. Interesting, a Chebyshev marking written here. This is an unusual filter structure. We continue. There's some biasing circuitry over there. Here's another pre-driver. And then finally, we come all the way at the top. Some more biasing here. Let me focus a little bit better. And there's the input. Okay, so we know that this path also works because we measured it and it doesn't produce anything. So if I go all the way back to the output, and let's think about this a little bit more. So what is going on here? So this is I think this is a pin diode switch structure. So we have the 3.2 gigahertz path here, which can flow. You can see it's on the outer ring here. So it goes over here on the outer ring, jumps here and can go to the output. And this pin can shunt it, and then this pin over here can be opened. So we either have this path active when this is turned off, or we have this path active when this is turned off. Now, since I see the voltage at the 3.2 gigahertz, it could be that one of these pin diodes is a problem and there's some leakage going through to the output. How can we find out? Well, we can measure this. We can indeed measure this voltage here and this voltage over here, which are accessible on the PCB. I don't need to measure them directly in here. Here's an access point right here. And here's an access point right here. We can verify that these signals are indeed complementary. And we can measure their voltage and see if they make sense and if they compare well with all the other signals that do the switching. So I'm going to close this up and put it back. Now I looked at this, I don't see any damage really, everything looks fine. So I'm not exactly sure what's gone wrong and if this pin diode is dead. Unfortunately, I don't have the instruments and the equipment to fix it, but I'm becoming more and more convinced that a wire bonder is something that I may need in the lab. So let's go and connect it back and see if these signals actually make sense and are consistent with how we think this thing works. So let's double check and make sure that we know which diode is causing the problem. We have a good idea, but I think it's good to verify regardless. So I'm going to turn the instrument on and everything is connected. You can see that we have the same output connected to this meter here. We're reading the 0.8 volt, that is the initial startup offset we see. And then I have my multimeter here, which I'm sharing the ground, and I can measure the two actual diodes and put the instrument in sweep mode, so it sweeps just below and above 3.2 gigahertz. So you should see those pin diodes switch right at that transition point between the two frequencies. Okay, so the instrument is in sweep mode, and if you pay attention over here, you can clearly see that this is going between -13 and 0.8. So we can go ahead and measure now exactly what those diodes voltages are and correlate them with this measurement. So I'm going to measure the diode on the 3 gigahertz path and check it out. When it's at -13, they're both at -13. And when it jumps to +14 to turn the diode off, we will actually get 0.8. That's because the other diode on the path is forward biased and is clamping that voltage to its forward bias voltage. So that means that we know which diode is broken. Now if I measure the other diode, the complementary diode, you can see that it's in opposite direction. That makes sense because when one path is enabled, the other path is disabled. So we are lucky in a way that these diodes are not DC coupled. Otherwise, they have a resistor in between them. Otherwise, they could damage each other. So having said that, well, obviously replacing this module would certainly help. But this diode that's on the 3 gigahertz path is not critical. We could remove it from the circuit and see how the instrument behaves. Obviously, it's not ideal, but it's just a shunt diode to remove the 3 gigahertz path when the other path is enabled, and that signal disappears anyway. So I think I'm going to go ahead and remove the wire, just remove the pin around this, and I'll show you that. And then that will disable the diode, and we can do a measurement again. And this would bring the instrument back to a reasonable state of usage, at least, until a replacement module is found. And I think that would be a good kind of halfway repair point. Okay, so here's the board. I've removed the RF deck from it. So this is the pin we're interested in. And I can unsolder this pin completely. So if you look, this is actually a socket. It's a one-pin socket. This is a really common technique that Keysight and HP has been using for years in order to attach PCBs to their metallized RF decks. So if I were to remove this, I can unsolder it, and then the pin will just stick through the hole in the PCB, and it won't make contact with anything. And that can be put back later if we ever change our minds. So that's the one that, of course, is suspect. Now here's the RF deck itself. Here it is. You can see all the different pins that would go through the PCB and through those sockets. You can also obviously cut this pin, but I don't want to do that because I don't want to modify this. And if later on we manage to get a wire bond and replace that pin diode, then we definitely don't want to modify this in a non-reversible way. Here we go. So now you can see when the pin is removed, it's not touching anything, so you can contrast it to the one above there. So this should be good enough, and this is very solid, so it really won't move around, it won't make contact, and even if it does, we'll just go back to where we were. So now we can put it back and do some additional tests. Okay, so I put everything back together now, and now we're directly measuring the output. The bias T is still there. I minimize the length of the cables. This is a V cable now, so you should have a much higher frequency response as well as a V converter here. So this is still a 26.5 gigahertz instrument, so we can go all the way to the higher frequencies. But first, let's see if indeed the problem of the voltage has been resolved after the changes I made. So I'm going to turn the instrument on, and check it out. There is no DC offset anymore. So the problem of that diode appears to have gone away. Now, how does the RF performance actually going to work? So we have to wait for the instrument to boot. Then I'm going to put it to 1 gigahertz, and that's where we were seeing minus 13 volts. That was the worst case scenario, so we can test with that. So the instrument is set to 1 gigahertz and 10 dBm, and there's already no voltage there. It used to be minus 13 volts, but I'm going to enable the output, and here's the output, and check it out. There it is, 1 gigahertz tone here at about 10 dBm, and you can see there's no voltage there. In between the frequency shifts, when the diodes turn on and off, there will be a brief DC voltage, which is a charge pushed through the diode, but that's okay. That's normal. That will go away. Charges the bias T and then discharges it very slowly because we have over here a 10 mega ohm resistor. So the discharge path is very long, time constant. So let's increase the frequency. Here's 2, here's 3, and then here's when the diode is going to switch. 4, do you see? We got a little burst of current there, and it's back to 0. And we continue, and I go all the way up to the highest frequency this instrument supports. There you go, 26 gigahertz. So it really does work. And that diode there, which provides some isolation at the lower frequencies and shunts the 3 gigahertz path, doesn't seem to cause too much issue. This over here that you see is a function of the instrument itself, I believe, because this path is open anyway. But nonetheless, obviously that diode is there for a reason, and removing it does affect the performance of the instrument, but it does bring it back to a functional point. So if you really want to get it working and you're desperate, this would work until you get a replacement module, or you can replace the diode yourself. So it looks good. Now we have to turn our attention and see what the problem with the OCXO is, where we got the YIG unlock loop condition. So here's the OCXO. I took it out of the chassis and plugged it in here directly. So this is still plugged into the instrument, and someone has already repaired this. You can see that the solder has been removed, and this has been completely disassembled, and it's now tapped closed. So I'm eager to see what they've done in there. So it's plugged in, and the instrument is turned off right now, and I've connected the output of this, which is supposed to be the 10 megahertz output, over here to the Roden-Schwarz oscilloscope. So I'm going to go ahead and turn the instrument on and see. We should see 10 megahertz there, and nope, we don't see anything. So yeah, it's not producing 10 megahertz, and it's probably why the instrument was having some trouble with the YIG oscillator locking. Perhaps it was trying to lock into this source and it couldn't. So obviously if this is not working, this is an option. So if this signal is not present, it will use some other 10 megahertz reference internally. This is for high stability reference option, which is this one has. So if it's not working, the instrument is still usable, but you shouldn't leave it connected in that case. So let's open it up and look inside. So here's the OCXO. I've opened it up, and it's clear that a lot of repair has already been done on this. So this is the cavity of the OCXO. This entire structure sits in here. I just removed it, and that's of course the oven, and is in order to be shielded thermally. This was quite hot when I took it out. So a few things to note here. This ribbon cable here that connects the front PCB all the way to the internals can become extremely brittle over time because it's so hot inside this. And obviously 2 of these pins had been broken. So whoever opened it most likely broke these during the disassembly because they were so brittle. And then these 2 wires simply replaced those pins, and so that's fine. I can see some wires here added that go inside this cavity and come out to the top, and the 2 transistors here and here have also been replaced. So the heater in this must have been broken. and someone has fixed that, so that's great. The heater does work, but of course there's no 10 megahertz output, so we have to investigate that further. I'd be shocked if this is fixable, because whoever did this obviously tried to fix the 10 megahertz also and has deemed it unrepairable, but we're going to try anyway. So the center pin over here is a 10 megahertz output that goes to this wire over here, and the ground goes to this wire over here. These two pins go over to these two connectors, go into a transformer. This is from Coldcraft, and then they connect into these pins that go into this chassis here. So we have to open this entire structure to see where these wires go and if there's any way to salvage the 10 megahertz output. And we can do measurements along the way, because this cable is luckily long enough that we can plug it into the instrument and work on this while it's plugged in, even though this would get ridiculously hot, so it would be a little bit difficult to work with. So let me go ahead and open this further, because it has 4 other screws, to take a look inside and see if we can trace these to anywhere meaningful. Okay, well, I found the problem. So here's what's going on here. This looks really messy, but it's easy to understand. So the heater is inside this block over here, and this block heats up, holding the crystal, keeping it at a constant temperature. So this has been repaired already. You can see the cable has been taken back out and taken in here and then to the transistor. So yeah, this is a nice repair job on that. So whatever has happened over here is being actually repairable. I'm not even sure how this was accessed. But in the meanwhile, it looks like whoever took this apart might have by accident destroyed the crystal core, because you can see there are some wires that would have gone from here to here, and this sits on top of this. But this is also screwed to the chassis. So if you are not careful, and when you unscrew this, you can twist the body of this and rip the wires off, which I think what has happened here. If you look carefully over here, you can see that those wires have been twisted and broken off. So yeah, that's the connection that's missing. Now, since we've come this far, I really don't want to give up. I wonder if I would be able to tap into these wires somehow and still maybe scratch off some of the epoxy that's there, create a little bit of room to solder to those cables and still make these connections and repair this, because it would be a shame not to do it since we've come this far. This is a variable capacitor, and that's tunable with a screw on the other side. That's how you tune these crystals with a screwdriver from the outside. Just very little, by the way, just maybe a few parts per million. There it is. So I'm going to try and see if I can fix this. The rest of it is pretty straightforward. It goes together like a sandwich, and we're just going to have to put it back. Okay, here we go. Some minor progress. I managed to get some wires on there. So one of them is actually the wire to the chassis, but it's really hard to solder to it. So I ended up just soldering to the pin anyway. So now we're going to reassemble this, and hopefully it will have some good performance. So here we are. I put it back in the unit temporarily here. It's not fully closed. I put the crystal back, soldered it, made sure the wires don't break again, and put it back together fairly carefully. These wires here are not added by the repair person. They're actually part of the heater, so they were always there. And the transistor obviously have been replaced, and these things that I talked about before. So I'm going to turn the unit on. I actually haven't tried this myself yet. So we're going to try and see if we get anything on there. So let me reposition the camera. Okay, let's turn the unit on. And it's on. It's not doing anything yet. Let's wait a few seconds. It may have to boot up before we get something. Let me see, what are we doing here? No, 50 millivolt. No, there's nothing yet. I wonder if it's not connected properly still. Let's give it a full boot. Ah, there it is. Look at that. Check it out. It is working. There you go. The unrepairable has been repaired. So yeah, so it seems to be working. So I think we should close it back completely before it gets too hot here, and then we're going to try and see if the frequency is accurate, and hopefully that fixes it. And here we are measuring the frequency of the oscillator. So I just turned everything on, and this is warming up and this is warming up, so you can see slowly climbing, and eventually it will stabilize, and it looks like it would stabilize fairly close to 10 megahertz. Now you wouldn't want to calibrate this like this anyway, because even the force of gravity, the direction of gravity, affects the crystal's performance. So you really have to have it in the unit, let it settle down for 30 minutes, make sure everything is really warmed up and this is the right side up, the instrument is sitting the right side up before you calibrate. But it looks like that it is working. At least I'm fairly confident that it can easily be adjusted and calibrated. So now we can put everything back together. Pooch, is everything working? Do you want to calibrate the crystal? Good, Pooch. And there you have it. I hope you enjoyed the repair of this Agilent E8257D. It was really fun working on this unit, and thanks to Altes for loaning this unit to me. I have left a link to their store and contacts in the video description in case you want to do some business with them. And thanks to all my Patreon supporters. I have some giveaways coming up. Just be a little bit more patient, and without you guys it really wouldn't be possible. Just the bias tees that connect to this, the 50 GHz bias tees, are super expensive, so really without your support I couldn't be doing these type of repairs for the channel, so I'm really grateful. So keep an eye out on the Patreon page. There will be some neat stuff coming soon, and I'll see you in the comment section.